Let's study 10th Standard ICSE Physics, Chapter 11, Calorimetry. Numericals of Section B. Let us start with the third sum. A molten metal of mass 150 gram, molten, that means it is in liquid state, is kept at its melting point of 800 degrees Celsius. And when it is allowed to freeze, that is a change of state is happening here, at the same temperature. Of course, during change of state or during freezing, temperature doesn't change. It gives out 75,000 joule of heat energy. So it's cooling, so it will give out heat. What is the specific latent heat of the metal? That is L. So let's solve the A part. Heat energy, Q, is equal to mass into specific latent heat. This formula is used whenever there is a change in state. And when there is a change in temperature, which formula do we use then? Well, then we use Q is equal to mCT. But here there is no change in temperature. Hence, we will use this formula. The heat energy is given. Mass is also given. So we have to find the specific latent heat. Now, since the heat was in joule and mass was in gram, the unit of latent heat will be joule per gram, which is not the SI unit. The SI unit is joule per kg, but they've not asked us to find in SI unit, so we can leave the answer like this. No need to convert here. Now in the B part, if the specific heat capacity of the metal is 200 joule per kg per Kelvin, how much additional heat energy will the metal give out in cooling to minus 50 degrees Celsius? So initially, it simply froze from 800 degrees Celsius to 800 degrees Celsius, from liquid to solid. Now in B part, it is in solid state, and now there will be a change in temperature. From 800 degrees Celsius, it will be cooled down to minus 50 degrees Celsius. In such a case, what is the total heat energy? How do we calculate that? Well, as I had mentioned, the heat energy is equal to mc delta T. Delta means the change in temperature. Mass remains the same, but notice that the value of C, specific heat capacity of the metal, is given as joule per kg. That means we will have to convert either the mass into kg or the value of C as joule per gram. So I have chosen to choose mass into kg. Often students forget to convert, and that is the number one silly error in this chapter, numericals. Also, I see that Kelvin is used, but when we subtract and find the difference in temperature, we don't have to ever convert degrees Celsius to Kelvin in calorimetry numericals at all, because this is a change in temperature. So if the change in temperature is 850 degrees Celsius, that is the same as saying the change in temperature is 850 Kelvin. So notice it's 800 minus 50. Well, use logic here. From 800 to minus 50, what is the total temperature change? Well, from 800 to 0, the difference is 800, and then 0 to minus 50, again a drop of 50 degrees Celsius. So totally it is 850 degrees Celsius. And then you solve and get the answer in joule, because the question is how much heat will be lost on cooling it. Next, the fourth sum, which is IMP. Mark it as IMP. A refrigerator converts 100 gram of water at 20 degrees Celsius to ice at minus 10 degrees Celsius in 73.5 minutes. Calculate the average rate of heat extraction. Well, heat is in joule and the rate is per unit time. So heat per unit time or joule per second is nothing but watt. So they've actually asked us to calculate the power. Power is equal to Q upon T here. And certain values are also given which will be useful for solving. Now, I feel that the best way to understand numericals in calorimetry is by drawing a graph diagram. It makes it so easy to frame sentences and to avoid any kind of confusion. So, after reading the question, I noticed that initially the water was at 20 degrees Celsius. So, first of all, its temperature dropped to 0 degrees Celsius. So, that is Q1 heat energy lost. Then it was cooled further, but this time the temperature won't drop. It is losing heat, but then it's simply freezing. So it will stay at 0 degrees Celsius and it will freeze. So that heat, the latent heat, is Q2. And after that, the ice at 0 degrees Celsius cools further to minus 10 degrees Celsius. The final state which is Q3. So the total heat released is Q1 plus Q2 plus Q3. So let's solve it separately. First of all, from 20 to 10 degrees Celsius, what is the heat energy released? MCT. I'm writing T1 simply because this is Q1. So mass is 100. C's value is given as 4.2 joules, but check the units. Yep, it is 4.2 joule per gram, and mass is also in 100 grams, so it is compatible. And the change in temperature is 20 degrees Celsius. So 8,400 joule. Next phase. The next phase is Q2 phase, the freezing phase. There is no change in temperature here, so the formula is ml. So mass, same mass, and the latent heat of freezing is given as 336 joule per gram. So the total heat lost here is 33,600 joule. And finally, the last phase of Q3, the temperature has changed of ice from 0 to minus 10 degrees Celsius. So what is the temperature difference? Obviously 10 degrees Celsius. And mass is same 100. Mass doesn't change even if ice melts or water freezes. But now the specific heat we will use is of ice. So I will denote it as Ci. Earlier we should have written this as Cw. Specific heat capacity of water is 4.2 joule per gram, but now it is in solid state, so its specific heat capacity has changed. Specific heat capacity of ice is just 2.1 joule per gram as given, per gram per Kelvin as given in the question. Yep, interestingly it's half of that of water. So multiplying, we get the total heat as 2,100 joules. So the total heat is the addition of the three, which comes up to 44,100 joules. That means the refrigerator took away 44,100 joule of heat energy to convert that 20 degrees Celsius water into minus 10 degrees Celsius ice. And how much time did it take to do this? It took 73.5 minutes. That's a lot of time. Perhaps that refrigerator requires some servicing. For SI units, we will convert it into seconds, and power, that is a rate at which the heat is being removed, is heat upon time, joule upon second, and the answer is 10 watt for the refrigerator. Now the sixth sum is also IMP. Find the result of mixing 10 gram of ice at minus 10 degrees Celsius with 10 gram of water at 10 degrees Celsius. Now it's interesting. So again, I have drawn a graph to understand this better. I have ice here at minus 10 and I have water at 10 degrees Celsius. Obviously this water is going to cool down as it loses heat, and the ice is going to heat up as it gains heat. So ice will reach 0 and perhaps water will also reach 0. But what is interesting is what will happen ahead. Will the water start freezing into ice, or will the ice start melting into water? And will it melt totally or partially? So I've put a dashed line here. Well, understand that the heat energy released by water here will be far greater than the heat energy absorbed by ice, because the specific heat capacity of water is high. Water is a heat reservoir and the masses are same as per this question. But again, the specific latent heat of ice is also quite high, so I don't think that there will be enough heat available for this ice to melt. Now one easy trick to remember is that in the numerical, if there is any mention that all the ice has melted or any indication towards it, only then we can be sure that all the ice will melt. Here there is no such hint given, so definitely the ice will only partially melt, not entirely. So there are many other sums where the hint is given or it's directly stated that all the ice has melted. Then we can assume all the ice has melted, and then the final temperature will be above 0 degrees Celsius. So remember this, if ice will melt only partially, then the final temperature has to be 0 degrees Celsius, which is obvious from this graph. You see, if the ice is melting only partially, this will stay at 0 degrees Celsius and the water will also stay at 0 degrees Celsius. If the final temperature was, let's say, 5 degrees Celsius, as mentioned in question number 8, that is a clear-cut indication that ice has melted, and in fact it's the water formed also heated up till 5 degrees Celsius. So we'll talk about 8th sum soon, but here definitely the final temperature will be 0 degrees Celsius and the ice will melt only partially. So the question is simply how much out of the 10 gram of ice will actually melt. So that's what this sum is all about now. So we start off with the opening sentence always. Heat lost by water is equal to heat gained by ice. By the way, the ice is gaining heat in two ways. First, to increase its temperature, and then to melt partially. So Q3 is equal to Q1 plus Q2. Q3, well, mass, specific heat capacity, and change in temperature. I've mentioned 3 just because it's Q3. Specific heat capacity of water, by the way. Q1, that is a heating up of ice, MCT. Note that the specific heat capacity of ice will be used here, not of water. Mass is the same, by the way, but still I used the term M1 because it's Q1, and delta T1 is 10 degrees Celsius difference here. And mass 2, I know that it is not the same as mass 1 because I know the entire ice has not melted, because if it were, it would have been clearly stated in the question. What about the latent heat? Specific latent heat, is it given? Yes, the value is given. So substitute all the values. The only unknown variable is M2. Get the value of M2, and it is indeed 0.625. That means out of 10 gram, only 0.625 gram of ice will melt. So this is the net final observation. By the way, what is interesting is how much water was left behind in the end? Well, it was 10 gram plus 0.625. So totally 10.625 gram of water was left behind in the beaker. And how much ice was left behind in the end? It was 10 minus 0.625, that is 9.375 gram of ice was left behind. And what was the final temperature? 0 degrees Celsius. Yes, it's a mixture of ice and water, and both are at 0 degree Celsius. If you supply more heat, more ice will melt, and if you remove the heat, then the water will start freezing into ice. So it's a reversible reaction. Next, the eighth sum, again IMP. Here we have water at 30 degrees Celsius, and obviously the copper vessel will also be at 30 degrees Celsius. No need to mention that in the question. Both are at room temperature, but the masses are different. Now I would like to cool them down to 5 degrees Celsius. So let's add some ice. How much ice? That we have to find out. But it is clearly given that the final temperature is 5 degrees Celsius. That's a huge hint, because if I draw a graph, I know that water's temperature has dropped from 30 to 5. That's a 25 degrees Celsius drop. Copper vessel's temperature has dropped from 30 to 5. That's again a 25 degrees Celsius drop. But what about ice? Initially we take ice at 0 degrees Celsius. Nothing is mentioned. So we'll take ice at 0 degrees Celsius. It will melt. It will melt, and it will absorb heat. It will absorb heat. But we want the final temperature of everything to be 5 degrees Celsius in the container, in the vessel. So obviously even this molten ice, that is water, will absorb more heat and rise to 5 degrees Celsius. So ultimately everything is at 5 degrees Celsius, which is what the question states. So this is possible only if entire ice melts. So you see here in the question it is indicated that the entire ice is melting. That means the mass of ice molten here will be the same as the mass of water whose temperature rose out here. So the heat lost by water and the heat lost by copper vessel is equal to heat gained by ice, which is in two ways, one for melting and one for increasing its temperature to 5 degrees Celsius. So change in temperature, so MCT, change in temperature MCT, change in state ML, and change in temperature MCT. Note I use M1, M2, M3, M4 just to correspond with Q1, Q2, Q3, Q4. And even with T1, T2, there is no T3 by the way, and T4 of course. Interestingly, T1 and T2 will have to be same because they have the same change in temperature. But still I used different variables, that's okay. Note here specific heat capacity of water is to be used. Here specific heat capacity of copper has to be used. Here specific latent heat of ice has to be used. And here again, by the way, ice had melted into water. So water's temperature is rising. So we will use specific heat capacity of water out here because Q4 relates to water's increase in temperature. It is no longer ice here. So all the values are given. Be careful about the units. Mass is in gram and specific heat capacities and all are also in gram, is it? Oh no, it's in kg. So what I did is I converted these values into gram here. 4200 became 4.2 joule per gram. 400 joule per kg became 0.4 joule per gram. And even here and here I have changed it. So again, a very silly mistake. If you don't convert the units and you lose 5 marks. whereas you could easily get full marks if you be careful about these few things. So the only unknown variable is this mass of ice. By the way, this mass and this mass has to be same, of course, because the ice has completely melted into water. So solve this and get the required answer. Note how I'm calculating. I'm keep bringing 25 out as a common, and I'm not multiplying it yet because I'll just push it down to the denominator and then I'll start cutting it. And this is a very difficult calculation, but you have to do it. Do not copy the answer. If you get the answer is 74.92, you can stop there. It's okay. 0.01 difference is allowed anyway. Next, the 11th sum. The amount of heat energy required to convert 1 kg of ice at minus 10 degrees Celsius to water at 100 degrees Celsius is totally 7,77,000 joule. Calculate the specific latent heat of ice. So again, the graph looks like this. We had ice at minus 10, its temperature rose to 0, then it melted at 0, and then its temperature of water increased to 100 degrees Celsius. So again, 3 distinct phases here. Let's solve them separately. Minus 10 to 0, there's a change of temperature of 10 degrees Celsius. Specific heat capacity of ice has to be used, and mass is 1 kg, so no conversion required here. 21,000 joule will be required for that. Next phase, melting. Q2. Well, that's melting, so there's no change in temperature, so simply ml. By the way, m is 1 kg, and L's value we don't know. That's the question. We have to find the value of L. I'm guessing it will be right, 3,36,000 joule per kg, because that's the value of ice. Anyway, the next phase is Q3. That is now the water, that is a molten ice, changes temperature from 0 degrees Celsius to 100 degrees Celsius. We don't have latent heat of vaporization. Anything to do with steam, we don't have. So even in the notes, if you read questions regarding steam, you can ignore it. It's not in our syllabus anymore. So Q3, again M, but this time we use CW, that is specific heat capacity of water, and change in temperatures, of course, 100 degrees Celsius, 100. So the final answer is 4,20,000 joule. The total heat energy is the addition of all three, whereas the total is given. The only unknown variable is L, so it is 3,36,000 joule per kg. Remember, specific latent heat is joule per kg. Be careful about the units being used. Now the 12th sum. 200 gram of ice at 0 degrees Celsius melts in 1 minute. So only change in state, no change in temperature. Next, there is a 200 gram of water, and we want to increase its temperature from 0 to 20 degrees Celsius. How much time will it take if we use the same appliance? Well, if you are using the same appliance, we can assume that the power will be same. So remember, that is how we will solve this sum, keeping in mind that power remains the same, power of the appliance. So first of all, the melting part. How much heat is required to melt it? Let's calculate using ml. So 67,200 joule. So what is the power of the appliance? Time was given 1 minute. So it's this upon 60 watt. I'm not going to solve it further because I can reduce later also. Next, there was water. Same mass coincidentally, but not necessarily. It was heated from 0 to 20 degrees Celsius. So how much heat is required for that? Using the formula and the values, we have 16,800 joule. How much time will be required for that? Well, first of all, the power in this case will be Q2 upon T2, and T2 we don't know. The time required for this case we don't know, but this is the power. Now we know that power in both the cases has to be same appliance. So the only unknown variable is T2. So now you know why I didn't divide it, because ultimately here I'm going to cut everything and get the answer, which is 15 seconds. Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.